All right, so let me start the second law of thermodynamics. Okay, so in the last lecture, you learn about first law of thermodynamics and then some thermodynamic processes. So today you are going to learn second law of thermodynamics. Okay. So the first law of thermodynamics tells about the conservation of energy. Okay. And then the second law basically tells about the direction of the thermodynamic processes. Okay. So before I go to the second law, the details of the second law, let me talk about something called reversible and irreversible processes. Okay. So the irreversible process is very common, okay, in our everyday life. Okay. And reversible process is basically almost impossible. Okay. In our everyday life, there may be some microscopic, reversible process in microscopic level, but macroscopic in our macroscopic life, I mean in our everyday work, reversible process is very rare. Okay. So what is the irreversible process? Irreversible process means it's not reversible. Okay, that means a process that can happen only in one direction. Okay. So for example, our life, okay, so it goes in only in one direction. We cannot go back to our childhood. So this is a very popular example of irreversible process. Okay. For example, if you break a glass, you cannot once it is broken, you cannot make it, you cannot bring it back to its the earlier position, right. So um uh, so these are the irreversible process. Okay. And it's very common in our everyday life. Okay. Now here, the irreversible process we already talked is the heat flow, heat transfer. Okay. So in the first chapter, or also in the second chapter, you learned that heat can transfer only from spontaneously from hot to the cold object, or hot place to the cold place spontaneously, right. I mean, that is the irreversible process, because heat cannot flow from the cold object to the hot object spontaneously. Okay. So this is another popular example that I'm going to use in this chapter to understand the second law of thermodynamics. Okay. So heat can only flow from hot to the cold object, naturally, but not from the cold to the hot object. Okay. But now the thing is, no physics laws can prevent the flow from the the heat flow from the cold object to the hot object. Okay. There is no law that can prevent it, but naturally it is not observed. Okay. So we need a physics law that can prevent it. Okay. And that's how the scientists come up with the idea of second law. Okay. Second law of thermodynamics. And second law of thermodynamics tells us that heat can only flow spontaneously or naturally from hot object to the cold object. It will not flow spontaneously from a cold object to a hot object. Okay. The next thing I'm going to talk about heat engine. And heat engine basically a device that converts heat energy to mechanical energy. Okay. And the development of the general statement of the second law of thermodynamics was partly based on the study of heat engine. That's why we are going to learn heat engine here in this the section of second law of thermodynamics. Okay. Some example of the heat engines are steam engine, and then combustion engine, turbine, etc. Okay. All right. All right. So okay. So here, this diagram on the right hand side shows the schematic diagram of a heat engine. Okay. So heat engine, as I already mentioned in the last slide, that heat engine can convert thermal energy to mechanical energy. Okay. Now, what are the essential thing in a heat engine? Of course, the system. Okay, we need a system. Okay, so the system is here. Okay, system is somewhere here, and it has two um, two reservoir. One is a high temperature reservoir at operating temperature TH. Another is low temperature reservoir at operating temperature TL. Okay, H means high, L means low. So high temperature reservoir at TH temperature and low temperature reservoir at TL. Okay, now when you add heat to the system, so let's say QH amount of heat is added to the system, some of the heat actually work uh, work on the surrounding. Okay, so I'm going to show a little bit better diagram for a heat engine in the next slide. Okay, so some of the heat actually work on the surrounding, and then rest are basically exhausted in the low temperature reservoir. Okay, so how much heat energy is exhausted? That is equal to QH, okay, that added heat minus the work done. Okay, so this is the relation between the QH, QL, and work done in a heat engine. Okay, now for a steam engine, the working substance or the system is the water. Okay, whereas in an automobile engine, the working substance or the system is a mixture of air and fuel. Okay, now before I go to the next paragraph, let me show you a, 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 a heat engine, how it works. Okay, so here in this pot we have water. Okay, and here we have a turbine. Okay, so when you add heat to the system, okay, you will see that added heat, the system basically does some work on the turbine. Okay, so you see that. I think you already see at some point in the first chapter, but again, here you see that. Okay, so the added heat, because of the added heat, the system does work on the surrounding. So here the surrounding is the turbine. Okay, so you see that how thermal energy is converted into the mechanical energy. Okay, all right. Now we are basically interested um, on the engine that runs in a repeating cycle. Okay, the benefit of engine that runs in a repeating cycle is the delta U is equal to 0. Okay, there is no change in internal energy. How? Let me show you how. Okay. Okay, so first let me show you how, and then go back to the last slide. Okay, so here you see that a schematic diagram is little bit a better schematic diagram for a heat engine where we use the repeating cycle. Okay, so here you see that in this boiler, so this boiler is basically the high temperature reservoir, and this condenser is the low temperature reservoir. Okay, so the system here is the water. When you add heat, okay, QH to this system, okay, so the water vapor does some work on this turbine. Okay, so W amount work is done by the system. Okay, and then QL amount of heat is exhausted in this condenser or the low temperature reservoir. Okay, now if we can collect the system from here and reuse it, okay, then the system does not have I mean, the system's U, the internal energy is constant. Okay, that means the water here is basically the same water what we use initially here. Okay, so that means if we can collect this water and reuse it, there is no change in the internal energy. Okay, that means delta U equal to 0. Okay, so when delta U equal to 0, from the first law of thermodynamics, we see that Q minus W. And if it is equal to 0, Q minus W, and Q minus W means Q equal to W. Okay, now Q is the net heat. Okay, now you know that in a heat engine we have two heat, QH, okay, and QL. Okay, so QH is entering the system, so it will be positive, and QL is leaving the system, so that will be negative. So the net Q is equal to QH minus QL, and that is equal to W. Okay, and in the last slide I also show a same equation. Okay, it was something like this: QL equal to QH minus W. So it's basically, these two equation is basically the same thing. Okay, so if you rewrite this equation, you can rewrite this equation and get the first this equation. Okay, so W equal to QH minus QL. Okay, for a heat engine, this is the equation. Okay, or this is the same thing. Okay, so here I also derive it. Okay, that is for repeating engine that runs on a repeating cycle. Okay, all right, now let's talk about the efficiency. Okay, so the efficiency of a heat engine is the ratio of the work done to the heat input. Okay, normally efficiency is the output energy divided by the input energy. So for a heat engine, the output is the work done, okay, and input is the QH. So this is the definition of efficiency for a heat engine. But W, you know, that is equal to QH minus QL for a repeating cycle. Okay, so our equation becomes something like this, and then if you simplify it, it will be something like this. Okay, so I mean, either this equation or this equation or this equation you can use to determine the efficiency of a heat engine. Okay, now the efficiency is I mean, in for a real engine, efficiency cannot be equal to 1. It is always lower than equal to 1. Okay, now why it is not equal to 1? Because it is impossible to have QL equal to 0. So when QL equal to 0, efficiency could be 1. Okay, so when QL equal to 0, if you plug QL equal to 0 in the efficiency equation, you see that efficiency is equal to 1 or 100%. Okay, but QL cannot be equal to 0. There is always some heat adjusted in the low temperature reservoir. Okay, and that's why for a real engine, okay, efficiency is always less than 100%, or less than 1. Okay, so yeah, here is a typo, it is not. Okay, for a automobile, normal automobile, I mean, for a car, normal car, the efficiency is 20 to 30%, 20 to 40%, depending on the car. Okay, all right, now let's talk about the Carnot engine. So Carnot engine is a theoretical engine. Okay, people, I mean, scientists use the Carnot engine theory to better understand the heat engine and the second law of thermodynamics. Okay, so it is an idealized engine which has no friction. Okay, and no Carnot engine is actually exist. Okay, So it's basically a theoretical idea. Okay, and here the process is reversible. That means if you start from a point A, you can come back to a point A. Okay, and how this happens? Okay, so um, you can explain the Carnot engine, or so this cycle is called Carnot cycle. So Carnot cycle is reversible process. You start from A and come back to A. Okay, so because you come back to A, it is a reversible process. Okay, now to do that, we need two expansion, two compression. Okay, so we need one isothermal expansion and one adiabatic expansion, and then one isothermal compression and adiabatic compression. Okay, so I can, instead of talking here, let me show the simulation. Okay, so here you see that the Carnot cycle in this diagram, PV diagram. Okay, so this line, so when it goes from this point, okay, from this point to another point. So let me check that whether I can use my pen. Okay, somehow I cannot use my pen here. Okay, so you see that the point on the red line. Okay, so let's start from that point. Let's say if you compare this with this picture, then this point is A. As it is going from this point to the next point in the high temperature line, okay, it's basically expanding, okay, and expanding isothermally. Okay, so when it expanding isothermally, it means that heat needs to get into the system. Okay, it is um, uh, heat is entering the system, and then that heat basically does some work on the piston. So here on the right hand side, you can also see that it is doing work on the system, and that means it is expanding. So you can see that. Okay, so you see that it is going up. Okay, because of the heat. um, um, and you see that this is the isothermal expansion, and the heat is basically doing work on the surrounding. Okay, and then the isothermal, so then adiabatic expansion. So adiabatic means Q equal to 0. That means at this time there is no heat exchange between the surrounding and the system. Okay, but still it's expanding. Okay, and expanding means adiabatic expansion means the decrease of the temperature. Okay, decrease of the temperature means the decrease of the internal energy. So here you see that that's why it's going from high temperature line to the low temperature line. Okay, and then you see that isothermal compression, and isothermal thermal compression means cooling, and at this point work is done on the system, and cooling means heat is leaving from the system. Okay, and so on, and the other black line is the adiabatic compression, and so on. Okay, so what we have to remember is, in a Carnot cycle, we have, it is a reversible cycle, okay, or a reversible process, and it has two processes. I mean, it consists two processes, isothermal and adiabatic, and two compression and two expansions. Okay, that's how Carnot cycle works. Okay, now the heat enters to the system is actually proportional to TH. Okay, so I mean, we need some equation to explain the theoretical efficiency or the ideal efficiency. Okay, and to do that we need this relation. Okay, so the temperature is proportional to the heat of the reservoir. Okay, the operating temperature TH is proportional to the the hot temperature, hot energy. I mean, energy at the, I mean, the heat at the high temperature reservoir, and similarly QL is proportional to TL. Okay, and these two equation tells us that QL over QH is exactly equal to TL over TH. Okay, and because of this, okay, the efficiency for the ideal or theoretical heat engine is equal to TL over TH. Okay, so you just plug this equation in the equation of the efficiency, and you get this equation. Okay, so this is the equation for the ideal efficiency. And again, ideal efficiency is 100% or 1 when TL is equal to 0K, 0 Kelvin. Okay, but 0 Kelvin is not attainable, it's not possible. Okay, 0K is not possible. Okay, so theoretically also theoretically also efficiency cannot be equal to 100%. It's always less than 100%. And this result is known as the third law of thermodynamics. Third law of thermodynamics tells us that 0 Kelvin is not possible. Okay, and because of that, ideal efficiencies cannot be equal to 100%. It is always less than 100%. So you see that theoretically even efficiency cannot be 100%. Okay, all right. And of course, this is the theoretical efficiency where the friction is ignored. And for real engine, we see that when scientists compare the Carnot engine and the real engine, they see that a well-designed real engine reaches 60 to 80% of the efficiency that the theoretical efficiency gives them. Okay, so for example, if if the if the Carnot efficiency is, let's say, 75%, okay, then um, then the if we think that the well-designed real engine have 80% of 80% of the Carnot engine efficiency, then the actual efficiency will be 80% of 75%. Okay, something like this. All right. The next I'm going to talk about refrigerator, air condition, and heat pumps. Okay, they are basically very similar. Okay, all right. So in heat engine, heat is going from hot to the cold. Okay, and while going from hot to the cold, the system does some work uh, on some external thing. For example, we see for a steam engine, it works on the turbine. Okay, but in refrigerator, air conditioner, and heat pump, okay, heat basically goes from cold to the hot. Okay, in this direction, but you know that this is not spontaneously or naturally possible. Okay, so to make it possible, okay, we need to do some work. Okay, because of the external work, heat can go from cold to the hot. Okay, it's not naturally. Okay, so don't confuse natural process and the artificial process. So here you have to do some work so that the heat can go from the cold to the hot place. Okay, for example, in a refrigerator, the refrigerator motor does work. That's why heat goes from the interior of the refrigerator to the outside. Okay, so let me show you here. So here you see, so this motor Okay, motor does some work, so you see that it is doing work, and that's why heat is going in this direction from cold inside to the hot outside. So this motor basically pumps the heat from the interior to the outside. Okay, so um, here, if you write the equation that connects the work done QH and QL from this arrow direction, you can write the you see that QL and W is entering the system, okay, and that is QH that is leaving the system. Okay, so again you see that it's the same equation, W equal to QH minus QL, right? In the heat engine you see the same equation. Okay, although the directions are different here, okay, direction for the QL, QH, and W are different, but you see the same equation also valid for refrigerator. Okay, now for refrigerator, we don't basically use the efficiency. Instead of using the efficiency, we are using another thing. It's called coefficient of performance, COP. Okay, so what is the COP for the refrigerator? COP for the refrigerator is again output divided by the input. Okay, so for a COP, for the refrigerator, the input is the work done and output is QL. So you want the interior refrigerator interior cold, right? So that's why the output here is the QL and input is the work done the motor does. Okay, now because W equal to QH minus QL, you can also use this equation for COP. Okay, and similarly ideal or theoretical COP is TL over TH minus TL. Okay, air condition is basically the same thing. Air condition and refrigerator works exactly similar way. So the COP for air conditioner is same thing for refrigerator. Okay, so you see that QL over QH minus QL. But the heat pump is a little bit different. Okay, so heat pump normally we use to to make the interior warmer, right? So although the heat flows in this direction from QL to QH in this direction because of this work done, okay, in this case the output is QH. We want our home interior, okay, inside the home warmer. Okay, so in this case the heat pump basically pump the heat from the outside to inside. Okay, so COP is different. So in this case it is QH over QH minus QL. Okay, so COP is because it is not the efficiency, it's the coefficient of performance. Okay, it is always higher than 1. Okay, normally it is between, for all, for refrigerator, heat pump, and air conditioner, the COP is basically between 2.5 to 3. Okay, and most heat pump can be turned around and used as a air conditioner in the summer. Okay, so same thing you can, normally it is you, heat pump, the same thing is used at heat pump during the summer, sorry, during the winter, and during the summer you can use the same heat pump as the air conditioner. Okay, you just need to turn the direction and you can make it heat pump or air conditioner. Okay, all right, the last thing I'm going to talk briefly is the entropy. Okay, so what is the entropy? Entropy is a measure of disorder of a system. Okay, measure of disorder of a system. Okay, and there is a I mean, in some textbook, people use entropy to describe the second law of thermodynamics. Okay, entropy, normally we use this symbol S for entropy, and mathematically the change in entropy is equal to this. Okay, so there is no simple definition for the entropy, but the simple definition for change in entropy is equal to Q is the heat, and T is the absolute temperature. So the entropy's SI unit is joule per Kelvin. Okay, so although it is the change in entropy. Okay, and the second law of thermodynamics tells us that delta S is always positive, is always greater than 0 for a natural process. Okay, so that means entropy is always increasing. Okay, entropy increasing means disorderness increasing. Okay, so a simple example is the mixture of milk and sugar. Okay, so when you, I mean, milk has it is ordered when it is separate from sugar, and sugar is also ordered. Okay, when you mix them, okay, they are disordered. The disorderness increases. Okay, what it means, it means no amount of energy, I mean nothing, it is, I mean, what I want to say is it is impossible to, I mean, once they are mixed, it is impossible to separate them. Okay, so I mean, when it is milk, it is ordered. When it is sugar, it is ordered. When they are mixed, they become more disordered. Okay, so once it is in the disorder state, it is almost impossible. I mean, it is impossible to make them separate. I mean, to make them go back to its to go back to their ordered state. Okay, and that is also the second law of thermodynamics, and it tells us that delta S is always positive, always greater than 0. Okay, so with this, I'm going to stop it here. Okay, the next thing is, in the next lecture I'm going to solve some of the problem from the chapter. Okay.